Today we're having a talk from Daniel Page, recent undergraduate from this university. He's giving his talk on enumeration of compositions, his honors thesis topic, and he is soon to be a graduate student here under Ben Lee. Take it away, Dave.
Hello, everybody. How's everybody doing? Okay. Awesome, awesome. So, anyways, as the title says, you can clearly see there's something about a restricted weak composition enumeration in here. But before I start, I just want to mention a couple things. When I say enumeration, I'm trying to aim mainly for generation of, say, combinatorial objects, because if you can generate it, most likely you can count it, just to get that confusion out of the way, because sometimes people will affiliate enumeration with counting. So today we're going to talk about what restricted weak compositions are and what kind of goals we would have for enumerating these objects. Now, there's some inherent flaws when it comes down to trying to generate these things, because they have some evil, underhanded kind of tactics they would punch into you if you try to naively enumerate these things. Now, aside from that, next there is going to be a talk a little bit. I'm just going to give two different methods that are more recent, and people like to use these a lot in algorithms to generate restricted weak compositions, or in case restricted compositions, or compositions, or any other type of composition. And you'll see a slow divergence away from very specific ones, more into these general ones. So thirdly, just some simple examples of generalized objects. Then I'm going to go into a quick example of the second order restricted weak composition generation algorithm. That one should go by a little quicker. And lastly, just some results. So there's the standard definition time. It is simple. What's going to happen is you're going to have a positive integer n, which is going to represent the number of parts of your composition. And s is going to be the sum or order of that composition. So when I say s or n, as you can see up in that up left corner, I guess, you can see sn at the bottom. Usually the s comes before the n. Sometimes people flip them in reverse, so be careful. But aside from that, they're just integer sequences stored as n tuples. In this case, we're only going to care about the n tuples because there are other types that deal with just no n tuples, just in general, sake of integer compositions. So here's an example here, where the sum is 3 and the length is, well, the sum is 4, length is 3. Where you can see all the sums here, so you can see everywhere it adds up to 4, but it only uses 3 positions to do so. If it makes it easier, just put plus signs between the commas and it might make a lot more sense. So next after that, I'm just going to use a little picture because it saves me a lot of time with explaining with formal definitions. So this is basically the equivalent idea. And these R1s just simply mean some subset of 0, 1, all the way up to S, where S is the sum. So as you can see here, here's R1 right there, and all these are identical to each other. So you can see it goes from 0, 1, 2, 3, all the way to S minus 1 and S, and it fills it up like a little equation. And that equation must add to S. So all the tuples that satisfy these positions will be in a weak composition. That includes 0. If I say just a normal composition, then it will not include the 0. So today I'm mainly focusing on the ones that include 0. So what's going to happen next is I want to define what a restricted weak composition is. So it's just any subset of a weak composition. So we're trying to find any particular subset. So when I have this guy right here, see if I wanted, say, these 3 right here, or some arbitrary set of them, say that guy, or maybe a cluster of 6 over there, this will be a restricted weak composition. By definition, even the set of a weak composition is a restricted weak composition. But there are some flaws with this, as you can read up here, which basically means if you can have a weak composition and you want to find any subset of that weak composition, including generating that object, you have to deal with big omega of n times the size of a weak composition. This is because you have to prune it, and these can grow exponentially, which is a huge problem when it comes to trying to find these little subsets. So that's a big omega there. I'll come back to that because there is actually a result that's the reason why that's like that. But anyways, as I mentioned, very inefficient if you want to prune every single one, because these sets can get huge. Because compositions have fun properties, but I'll mention that a little later. But the idea is we want to find some superset so that we can prune any given subset and find the one we want. So we're going to try to find the smallest possible subsets to start pruning them, because we don't want to prune every single one, because who knows, there could be millions of them. So what I'm going to do is I'm just going to take it one step further, and I'm going to show you that I can make the smallest possible one over parts. So each one of the positions. So I'm just going to introduce two techniques just because these are really popular in the literature lately. But one technique here is called the loopless algorithm. These have been around for a while, but the structure is very simple. It takes linear time to create the first object. And then after that, you have to take exactly constant time, so asymptotically constant, so you can take 10 steps, maybe 15 steps, maybe even 1. But you have to create the next sequence from the original, but in some instances, you do not want any extra steps, and the ones I'm really focusing on here are loopless gray code algorithms, which will make one change at a time, no more than one. Now, a lot of recent algorithms on this topic will use loopless gray code algorithms. Now, another technique I want to show you is that you can turn certain objects into the other types of objects we may be looking for. In this case, a weak integer partition, which is very simple. It's the same idea, except the order doesn't matter. So the natural thing to do is you want to just permute all the positions. By doing this, see, as our example here, sum of 4, and you have 4 positions here. If I do the example, I could permute them all and find the weak composition by just simply permuting them all. As I just noted down here, in 2008, somebody did develop an algorithm that does this, except it uses loopless gray code algorithms. Now, I want to pull in a couple very recent developments in this field, mainly enumeration, but these are the kind of supersets you'd be using, but I'm going to show you I can do even better than this. So this one was in 2000 by Timothy Walsh at University of Quebec, sorry. I'm kind of rambling sideways. So this is a little different here. Notice that instead, each one of these is going to be a different set. And it's just going to be denoted by that Rn2, which is a second order restricted set. So that's just going to be a bunch of n tuples, and each one will store, actually no, there'll just be sets. And each one of these will store certain selections based on whatever you want in each position. So now you get more selection. Now this result, by Timothy Walsh, you get from 0, 1, 2, all the way up to any mi, which is between 0 and s inclusively, which is a really big result. In fact, the algorithm that he uses is based off of Klingsberg's algorithm in 1981, where instead he augments one part of his algorithm so that he can get big O of 1 operations using the gray codes. And now almost all results in loopless gray code algorithms that will work on compositions will use that result, most likely, because it's big O of 1 to generate each sequence. Like, how much better can you get? So another one right here is just in 2009, Jay Updike. If you ever use MATLAB, there is a method in there for integer compositions. This is the guy that's sitting inside of there. So this one is just a bounded composition, but keep in mind this is not a weak composition because it allows only 1 and up to s. And you have to define L and U as your bounds. So you can generate all the objects, but they have to be the same in this case. So that's why there's no added index on the bottom. Now this one is the one that's really interesting. In 2011, these two nice fellows here developed a really, really good loopless gray code algorithm that generates not only just a restricted weak composition of some sort of bounding, but it can do it from both sides. So it can do it from lower and upper bounds. But with that in mind, you can do this. You can start from the bottom, but you can assign each one with a cap on top, but it must be less than or equal to u. So the closer you get u and l together, the better the algorithm gets. So just a little tidbit. Now, that's the most recent result. But all I'm going to introduce is 2 more combinatorial objects, just because these are really generalized compared to even these. So I'm going to introduce one of these, one of these is the first order restricted weak composition. Now this is an object that looks quite similar to the Updike object I just showed you, where all of them are the same, except now this time you're allowed to pick any arbitrary subset of 0 up to s. So now in this case, you can do all sorts of things with this. Now I'm going to take it one step further, and I'm going to take it to the second order, because this is really just a special case of what I'm going to really tell you about. This is the second order restricted weak composition. Now this object here, on the other hand, allows you to restrict on each part or position, well, you're allowed to pick any arbitrary subset. Now this is a really, really general type of object, and naively you can get yourself in trouble with developing an algorithm for this, because it inherently looks similar if you only included non-negative integers to something like subset sum. But you have to keep in mind the maximization, minimization property. That's something else. But that's the main object I'm interested in right now. But the problem I have at hand is I want to generate that second order restricted weak composition. And my claim is I created it. So I'm just going to give you an example of this, but I just want to mention one other thing. This involving the theory around these kind of algorithms is, actually I developed this algorithm out of a context-free grammar. Now this grammar has a couple interesting properties to it, is that following 3 axioms that I defined for weak compositions, I was able to find the smallest restricted weak composition subsets using a context-free grammar that minimizes the product of the variables and, lastly, the terminals. So you can make this really small with small production rules and small variables and small terminals. In fact, it looks a lot like a Chomsky normal form, which is really neat. Now, other things I've proved that the weak composition is regular. That one you can get from a variety of theorems. Because it is a context-free grammar, there are these things called right linear grammars, and all the production rules of my context-free grammar get you a right linear grammar, thus you can make it regular. And that makes a couple assumptions and allows you to do a couple more things, which I'll show you in a bit. But in a little bit more of a higher level sense. And there is the correctness of this algorithm. I did prove the correctness of it. And lastly, there is the worst case time and space complexity, which are big thetas. So what I'm going to do is before looking at that, I'm just going to mention a couple things. So watch very closely what I'm going to do. So this algorithm will take in as input S as the sum, N as the length, and that nasty R62, which means that the length is 6. So it means it's a 6 tuple. Now what's going to happen is, unlike the loopless gray code algorithms, which will generate one sequence at a time, what my algorithm does is it starts and tries to generate them from left to right. So doing so, you actually can construct sequences that are actually subsets of the actual weak composition that you're looking for. So you have different sums at given points when you're adding integers into your sequences. So what am I going to use to store these? Well, I'm going to use some queues. Now you might see in a little bit why I chose queues, but you can also use a stack if you wanted to. As long as it's a linear data structure, which I can take one end out and put one in, it should work just fine. But aside from that,